Welcome to the Explainer. Look, today we're doing a forensic autopsy on a silent, system-destroying anomaly. I'm talking about thread pool starvation. It's this hidden back-end killer that can take down massive distributed systems without making a sound. We're going to tear it apart, look at exactly how it works under the hood, and walk through the intense, highly practical fixes you absolutely need to bulletproof your architecture. All right, let's just jump right in.
We're starting with a real-world postmortem straight from the engineering trenches. Picture this, okay? It's 3 a.m., your production system completely crashes. The APIs, totally unresponsive. But here's the bizarre part. Your traditional metrics, like CPU usage, they look perfectly normal. Actually, CPU utilization dropped to near zero. It wasn't until the engineers frantically pulled thread dumps that they found the real culprit, thread pool starvation, completely triggered by unbounded blocking I/O operations.
So you've got to ask yourself this crucial question. Why on earth did the entire backend stall out when the CPU was basically just sitting there idle? It feels like a total paradox, right? Well, to solve this mystery and catch our killer, we have to look way past the illusion of a healthy CPU metric and dig into the actual nitty-gritty mechanics of concurrency in your application.
Section 1. Anatomy of a thread pool. The core mechanics.
You know, a lot of developers really misunderstand this fundamental relationship. You've got your core pool size and your maximum pool size. Core threads, they're kept alive to handle your baseline, everyday traffic. The maximum size, on the other hand, dictates the absolute hard limit of concurrent worker threads that are allowed during massive traffic spikes. People usually just assume that threads simply scale up immediately as traffic increases. Actually, scratch that. They assume the system just magically handles it. But the reality of how something like the Java thread pool executor handles this is way, way stricter. Let's walk through exactly what happens when a task arrives. Step 1, it gets assigned to a core thread. Simple enough. But if all those core threads are busy, it does not immediately spin up a new thread. No way. Step 2, it's shoved into a queue. Step 3, only when that queue is completely 100% full will the system finally panic and spin up new threads up to that maximum limit. And then step 4, if those max threads are hit and the queue is still full, the task is flat out rejected. Now, keep that queue step in mind, because that is exactly where the murder happens.
Section 2. Cause of death. The blocking I/O bottleneck.
We really have two distinct models at play here. On one side, you have traditional synchronous thread pools. These allocate one dedicated thread per request. If that thread needs data from a database, it literally stops and waits. It does zero CPU work. It just hogs the memory and sits there waiting. On the flip side, you have asynchronous event loops, like what you'd see in Node.js or Java's Netty. These use non-blocking I/O. A thread fires off a request and just immediately moves on to handle something else. It gives you super high concurrency with incredibly low overhead. When you use that synchronous model for heavy I/O workloads, you are practically setting a trap for yourself.
And here's the domino effect in action. Say your database connection pool gets exhausted, or maybe a downstream service slows down by just, a few hundred milliseconds. Suddenly, your active core threads get stuck waiting for that I/O. They are literally being held hostage. Because they're stuck, new incoming requests start piling up into the queue. And if you made the architectural mistake of using an unbounded queue, meaning a queue with absolutely no size limit, that queue just fills silently and endlessly. The JVM won't spawn any max threads because, hey, the queue technically isn't full yet. So your backend just starves to death, your memory fills up, and your CPU sits at zero because absolutely no threads are actually executing code.
The symptoms of this kind of starvation are just catastrophic. You'll see your 99th percentile latency suddenly spike exponentially. Entire API endpoints will just become totally unresponsive. You get that paradoxical drop in CPU we talked about, and what's even worse, as engineers over at Uber have noted in some of their postmortems, these failures usually manifest during really high-stress events like data center failover drills. You get these sudden traffic shifts hitting a new data center, the connection pools get overwhelmed, threads block, and boom. You get a devastating cascading failure across systems that weren't even part of the original problem.
Section 3. The toxicology report. Detecting the killer.
Look, you cannot rely on basic CPU monitoring here. It's gonna lie to you. You absolutely must rely on rigorous forensic profiling tools. Things like Java Flight Recorder and Visual VM are just essential. You need to be pulling thread dumps right in the middle of these stalls to expose exactly which blocking database calls or network requests are hoarding your worker threads. Plus, you should be piping metrics on your active thread count and your queue depth directly into something like Prometheus. If your queue depth is skyrocketing while your active threads are maxed out, your system is starving. Period.
The absolute most important number for catching this anomaly is 99. You have to aggressively monitor your 99th percentile or P99 latency. Let me tell you, average response times are a complete lie in distributed systems. Averages are just going to hide those localized stalls caused by thread starvation until it is way too late to fix anything. If just 1% of your users are experiencing 10-second delays because of blocked threads, your P99 metric is going to be screaming at you, while your average latency might barely even budge.
Section 4. Preventative Medicine, Practical Fixes.
All right, these are your absolute non-negotiables. First, never ever use an unbounded queue in production. Just don't do it. You must strictly cap your queues to prevent memory exhaustion and basically force the system to handle the load correctly. Second, isolate your blocking tasks. If you've got legacy blocking database interactions, you need to move them into their own isolated, dedicated thread pools. That way they don't starve the threads that are trying to serve your fast HTTP responses. And finally, wherever humanly possible, migrate over to non-blocking asynchronous I/O.
Now, if you limit your queue, like we just talked about, eventually it's going to fill up, right? When your bounded queue is full, you have to intentionally define a rejection policy to enforce system back pressure. You've got a few options here. Abort policy just throws an exception, which is great if you need to fail fast. But caller runs policy, man, that is a brilliant mechanism. It literally forces the thread that submitted the task to execute it itself. This creates natural back pressure, physically slowing down the rate of incoming requests instead of just crashing the whole server. So choose your policy intentionally.
And please, stop guessing your pool size. For I/O-bound tasks, you need to calculate it mathematically. There's this golden sizing formula derived from Little's law. It's simple. Optimal threads equals your hardware cores multiplied by 1 plus the ratio of your blocking wait time divided by your actual service time. This brilliantly accounts for the blocked state of threads, ensuring your CPU remains perfectly busy while other threads are off waiting for network or database responses. So measure your wait times, run the math, and tune it precisely. No more guessing.
Section 5. Mechanical Sympathy, Beyond Thread Pools.
But what if you need to go even faster? Say you're in an ultra-low latency environment. Think like high-frequency trading. In that world, even a perfectly mathematically tuned thread pool is just way too slow. Standard architecture completely fails. Enter the LMAX disruptor. See, in high-frequency trading, standard bounded queues fail because of lock intention. You get two threads trying to read and write to the same queue, and they just lock up the system. So engineers invented the LMAX disruptor pattern. It uses this pre-allocated ring buffer, and it exchanges data between threads using single-writer, multiple-reader coordination. This entirely eliminates the need for locks, and because all the objects are pre-allocated, it practically bypasses the garbage collector entirely. It's genius.
The disruptor achieves what we call mechanical sympathy. It genuinely understands how the bare metal hardware actually works. Modern CPUs, they update memory in 64-byte cache lines. If you have two threads updating different variables that just happen to sit on the same cache line, they cause constant cache invalidations. It's a massive performance killer called false sharing. Well, the disruptor elegantly solves this by padding memory with dummy variables. This ensures that your hot sequences sit perfectly isolated on their own dedicated 64-byte cache lines.
And what exactly is the result of that mechanical sympathy? 25 million. By stripping away standard queue locks, completely avoiding garbage collection overhead, and actually respecting CPU caching architecture, the LMAX disruptor pattern handles over 25 million messages per second, with nanosecond latency. Nanosecond. That is the sheer power of moving beyond standard thread pools and truly understanding your hardware.
Which brings us to the final most important question you need to ask yourself today. Are your thread pools strictly mathematically tuned for your hardware's workload based on wait and service times, or are you just using unbounded queues, totally guessing at your limits, and essentially just waiting for the next 3 a.m. crash? Seriously, take a hard look at your codebase today, check your queue limits, isolate that blocking I/O, apply those formulas we talked about, and stop letting thread pool starvation be your hidden back-end killer. Thanks for joining me on this explainer. I'll see you next time.